This video will discuss how to graph radical functions. So first of all, when we graph, we make a table. Now, earlier in this class, we had a lesson at the very beginning of the semester on how we can just look at the equation and envision what the graph will look like without even graphing it. So, for example, if we had y equals 2x plus 3, this is from the class before this class that you're in. You learned to graph this. You would go to positive 3 on the y-axis. This is your slope, so you'd go up 2 and then to the right 1. And it would end up making some sort of line. Okay. And then each different function, depending on what the function looks like or what the exponent is, would make a different looking graph. For example, we learned that when we had an absolute value equation, that's where it's going to make the v-shaped graph. And we talked about if the equation's highest exponent is a 2, it's going to make the parabola-shaped graph, and so on. So if you look at the square root of x minus 2 and you do not know what that graph is going to look like, when you pick your x values, you want to space them out so you get a good overview of what the graph will look like. So you don't want to pick 1, 2, 3, 4, 5 all the time. You want to spread them out if you don't know what the shape of the graph will look like. Now, in addition, you have to pick numbers that when you plug them in is going to give you a value you could have in the radical. So, for example, let's pretend I were to pick the number 1. So if I were to plug in 1 for the x value, I would get 1 minus 2 is negative 1. And then we can't do that. If we put this in our calculator, the square root of negative 1, it's going to say error. So we can't pick that value. So instead of plugging in numbers to find out that they don't work, the first step when you graph is, even though it doesn't ask for the domain, you want to think about what numbers are you allowed to use for x, because that's what domain means. What can we use for x? So to find the domain, since the index is even, it's a 2, you take whatever's inside the radical, so the x minus 2, and you say to yourself, it has to be a big number. The smallest it could equal is 0. And then we solve this. And we find out that the smallest number that x can equal, that's what this line means, is 2. So the smallest number I can use is 2. So I want to start with 2, and then I'm going to pick any number that's bigger than 2. So let's say I pick 3. Okay? And then I could pick 4 and 5 and 6, whatever number I want. I could pick 2.5 if I want, as long as it's 2 or greater. So then I'm going to go ahead and now, instead of picking 1, I'm going to go ahead and plug in 2 for x. So remember our function was the square root of x minus 2. So instead I chose to plug in 2. So if I plug in 2, I'd get 2 minus 2 is 0. That number is okay in the radical. The square root of 0 is just 0. So now we have our first ordered pair, and we can go ahead and graph that. It's at 2, 0. There's our first ordered pair. And then let's say I plug in 3. So if I choose to plug in 3 for the x, 3 minus 2 is 1, and the square root of 1 is 1. So now I have my next point at 3, 1. So right there. So if you only have 2 points, you can't tell what the graph looks like. So you need to plug in more and more values so that you get a better picture of what the graph will look like. So then let's say I plug in 4. So now I'm going to plug in 4 for x right here. 4 minus 2, and that's 2. And then the square root of 2 is a decimal. Square root of 2 is going to be it's going to be 1.414, all those numbers, so it's about 1.4. So I'm going to go ahead and put that it's about 1.4. Plug in 4. So I'm going to go to 1, 2, 3, 4, and I'm going to go up 1 and almost halfway, so about right there. And now those points are really close, so if I don't know if the graph's going to go up or down, I don't know what it's going to do. I don't want to keep picking 2, 3, 4, 5, 6. I want to space it out. So maybe I'm going to plug in 10. I want to see what happens when I plug in a number all the way over here. So now I'm going to plug in 10. I'm going to take out the x. And you again can pick any number 2 or greater. Now I'm going to plug in 10. And I get the square root of 8, which that's going to be a decimal number. So I'm going to plug in the square root of 8, and that's going to be about 2.8. So it's about 2.8. I'm going to go up to 2 and almost to 3, so about right there. So again, if we don't know what this graph is going to look like, we need to pick more numbers. Now, I'm not going to pick any numbers over here, because our domain says if we plug in any number over here, no. If we plug in any of these numbers here, it's going to make the number inside the radical negative. So that's why I'm just picking numbers over here. Okay, so now I'm going to go ahead and pick, so let's say I pick 6 for x. When I plug in 6 for x, I'll get 6 minus 2, which is 4, and the square root of 4 is 2. So you could pick the numbers you want for x. So if you know and you just think about, well, what number could I subtract 2 from so it makes it a perfect square, you could pick numbers like, for example, 18, because 18 minus 2 is 16. You would just have to extend your graph. So we get 2. So 1, 2, 3, 4, 5, 6, and 2. So now, that's not enough points. Again, is it going to go down? Is it going to go up? So that is what we use a graphing calculator for. So we can see if we add an infinite amount of points, what the graph is going to look like. So I'm going to go ahead and show you what this graph looks like on a graphing calculator so we don't have to plug in more numbers and we can just see what the graph will look like here. Okay, so if we take a look at the graph for this, you can see that it's going to start here, because any number on the left here is going to make it negative inside. And then it kind of curves like this, keeps going and going and keeps going up and up and up. So that's how I know when I graph this, when I connect it, that I'm going to make it curved like that. And then I'm going to put arrows to show that this is going to keep going and going and going and going. And then I'm not putting an arrow here because it doesn't keep going. It stops right here. Okay, so if I want to get full points on an exam for a problem like this, there should not be an arrow on this side. There should be an arrow here, and this should look curved. It should almost look like a U sideways and only half. So if when you connect them, yours looks like this, that's not good. No. It should look curved. Alright, let's go ahead and take a look at the next graph. So the next function we're graphing, the index here is odd. So the first thing we want to do is think about what numbers we're allowed to plug in for x. So that's called the domain. And when the index is odd, we can plug in any number we want, whatever we want. So if I want to plug in, for example, -1, I could plug in -1. If I want to plug in -10, I could plug in any number I want for x. So I'm going to go ahead and start with those two. So the function f of x equals the cube root of x plus 1. Now I'm going to go ahead and again, you can plug in whatever number you want. So I'm going to go ahead and plug in -1. And then -1 plus 1 is 0, and the cube root of 0 is 0. So I have now this point right here on my graph. Now I'm going to plug in negative 10 for x. Negative 10 plus 1. That's negative 9. And then what times itself 3 times is negative 9. So that's going to be some decimal number. So I'm going to put in the cube root of negative 9. And it's about negative 2.1. So about negative 2.1. So about right there. Okay, so we're going to plug in whatever numbers we want. If I don't know what this graph is going to look like, I want to pick numbers so that they're all throughout the graph. So I could pick any numbers I want. So maybe now I go plug in 10. I want to see where the graph goes on this side. So now I'm going to plug in 10. So the cube root of 10 plus 1 is the cube root of 11. So what times itself 3 times is 11. That's about 2.2. So about 2.2. So I'm going to go to 10 and up to just a little bit more above it. Okay. So now maybe I'm going to pick something in the middle here. So maybe I'll pick 5. Now I'm going to plug in 5 for x. And we would get the cube root of 6. So what times itself 3 times is 6. And that's about 1.8. So about 1.8. See how these are coming out to be decimals? If you don't want that, then you should pick a number like, for example, 7. Because 7 plus 1 would be 8, and the cube root of 8 is 2. So 7 would have been a good number, and you would have gotten 2. So I'm going to go to 5. 1, 2, 3, 4, 5, and go up to almost 2. And since I did 7, might as well add that one to our graph. So 7 is 2. Okay, so now I want to see where the graph goes here. So maybe now I'm going to pick, I don't know, negative 4. So now I'm going to plug in negative 4. And we get the cube root of negative 3. So what times itself 3 times is negative 3. And that's about negative 1.4. So about negative 1.4. So I'm going to go to negative 4 and go down 1 and almost halfway. So now at this point I'm like, what is this going to look like? I have no idea, right? We only plugged in 6 points. So that is where we go to our graphing calculator that will graph infinite amount of points and put it in our graphing calculator. And there's what this graph is going to look like. So I know when I connect these points that it's going to go up like this. Oops, like that. And then it's going to go like that. So when I connect them, I want to make it look like this graph here. Okay. Alright. So then if we look at our last graph, the index here is even. So since the index is even and it's a 2, it's going to look like this graph, not like this. Because the index is even, the first thing we have to think about is what is our domain. So we know that whatever's inside the radical, so this minus 4 is not in the radical. This line does not go over it. In other words, it is not saying this. It is not saying f of x equals the square root of x minus 4. See the difference here? This is inside, this isn't. So when we find the domain, whatever's in the